Welcome to Chapter 5. And so today is approximating areas with rectangles, sigma notation, and Riemann sums. And here's an applet you can use for a few of your homework problems. Okay, so let's start with approximating area. Suppose we want the area underneath this curve here. One really crude way to approximate that area is to compute the height of the curve at C1, that would be f of C1, and multiply by the length of the interval from A to B, that's B minus A, and that would give us the area of this whole rectangle, and that would approximate the area underneath the curve. If we wanted a slightly better approximation, we could break the interval from A to B into two subintervals, each having the same width of delta x, and we could use two rectangles. The first one would have height f of C1 and width delta x, so that would be area f of C1 delta x. The second one would have height f of C2 and width delta x. That would be the area, add them together, and it would be a slightly better approximation. You do not have to determine the height of your rectangle by the midpoint. So here are three different pictures where I've used four rectangles to approximate the area. And if you can look at each picture, in this picture, it looks like the height of each rectangle is determined by the value of the function at the midpoint of each subinterval. So this would be midpoints. And in your homework, you'll be asked to approximate areas using either midpoints, left-hand endpoints, or right-hand endpoints. So let's take a look at this next picture. This first rectangle has height determined by f of C1. That's the right endpoint of this first subinterval. The second rectangle has height f of C2. Third one has height f of C3. And the fourth one, since this graph crosses the x-axis here, this fourth rectangle is what we call degenerate, got zero area. So this is an example of right endpoints. And then finally, if we use left endpoints, we get our degenerate rectangle over here, and then we get these rectangles. So this would be left endpoints. Okay, so let's practice doing this by hand with some actual examples. Divide the interval from 0 to 4 into 4 subintervals and approximate the area using left-hand endpoints. Okay, so the formula for delta x, that's the width of each subinterval, is b minus a over n. Now, we don't really need a formula to figure out the width of each subinterval. If the whole thing goes from 0 to 4 and we want 4 subintervals, each one clearly has width 1, but let me just show you how that works. B is 4, A is 0, and we're going to divide by n, which is 4, so that's 1. So each of these subintervals has width 1. Okay, we want to determine the height by using left-hand endpoints. So we go over here to our first subinterval. The height of the curve at 0 is 0, so that's going to give us a degenerate rectangle. Our next rectangle will have height f of 1. So it'll go across like that, down, there it is. Next rectangle has height f of 2, so that will look like this. And the last one has height f of 3, which happens to be the same as height f of 2, but that's okay. We just go across, come down, and sketch. So it looks like we've got some overlap on the right and some underlap on the left. So let's compute that area. The true area underneath the curve is approximately f of 0, that's the height of the first rectangle, times its width, which is 1. Next rectangle has height f of 1, has width 1. They all have width 1. Then f of 2 times 1 plus f of 3 times 1. Now let's put in some numbers. That's 0 plus f of 1 is 6. I've got the coordinates on here. And then f of 2 is 12. And then f of 3 is also 12. So that's 30. Okay, let's do it again. Same picture, same function, same number of subintervals. So delta x is still 1. But now I want to use right endpoints. So the height of the first rectangle, instead of being 0, the height of the first rectangle is going to be 6. So go to 6, draw across. There's your rectangle. Height of the second rectangle is going to be 12. Height of the third rectangle is 12. height of the fourth rectangle down here is 0. So our degenerate guy is over here. And so the area is approximately, the height of the first rectangle is f of 1 times the width, which is 1, plus f of 2 times 1, f of 3 times 1, and now we're going all the way to f of 4 times 1. So I still have 1, 2, 3, 4 rectangles like I did above, but the heights are determined at different points. All right, so this is f of 1 was 6, and then 12, and then 12, and then f of 4 is 0. I'm still getting 30. And that's not always the case. Sometimes you'll do right and left, and it will be a different number. So it's just coincidence that we're getting the same number in each case. Okay, so some of your homework problems get a little harder in terms of arithmetic. So we're going to do the same. I'm going to show you the same setup, except now we're going to use midpoints instead of left-hand endpoints and right-hand endpoints. And you can see from my picture, I've already drawn in our rectangles, but you can see from my picture that the algebra is going to get kind of ugly. The area is going to be approximately f of a half times delta x, which is 1, plus f of 3 halves times 1, plus f of 5 halves times 1, plus f of 7 halves times 1. Now, there's really no need to do all this by hand. Let me show you how Desmos will do this. It's really amazing. I've got the curve already put in. So you'll have, when you do yours in your homework, come up here and you can put your function in up here at the top and then set your left-hand endpoint, your right-hand endpoint for whatever interval you have, and then the number of subintervals you want. And then how do you determine middle, left, or right? That's C. And the instructions are right here. C is 0 for left, 0.5 for midpoints, and 1 for right-hand endpoints. All right, so I've already put our function into this one, and you can see that the picture agrees with the one I had on the lecture notes. I set A equal to 0. I set B equal to 4. I set N equal to 4 because I want 4 subintervals. And I wanted midpoint, so I set C equal to 0.5. And if I'd wanted left, I'd set C equal to 0, and I would have gotten 30. And we did that by hand. We got 30 for left. And so now we're going to have Desmos do the arithmetic for us. For midpoints, we get 33. So we don't have to add up all those numbers by ourselves. This box right here will give you the sum. So that's 33. Okay, a lot of adding goes on, right? I only use 4 rectangles, but what if I had 30? Well, that's kind of a hassle. Well, it's a hassle. It's also a blessing. The more rectangles you use, the less error there is. If you can see this, got a zillion rectangles. And I can see there's very little error, very little underlap, very little overlap. So that would be probably a pretty good approximation for the true area under that curve. But we need to talk about a way to add up a bunch of numbers without this. This is called as ellipses, the dot, dot, dot. It's a little bit vague, okay? So what we do is we use summation sign. This is a capital sigma. It's a Greek letter, like from a fraternity. And the bottom number is where you start. The top number is where you end. K is called the index. You don't have to use K. You can use I or J, but this means add up for K going from 1 to N. So if that's confusing, let's do an example. Let's do this one. Add up K squared plus 1, K equals 1 to 3. All right, so this is equal to, when K is 1, you don't have to put what value of K is underneath. I'm doing that for you. When K is 1, I get 1 squared plus 1. Then I'm going to add on the value when K is 2. When K is 2, I get 2 squared, which is 4, plus 1. Then I add on K equals 3. 3 squared is 9. 9 plus 1. And I stop because I'm only supposed to go to 3. All right, and I add those together, and I get 17. Okay, let's do another one. K equals 1 to 4 of the number 3. This one's confusing because there's no K in the formula, but that's all right. When K is 1, the formula says 3. When K is 2, the formula says 3. When K is 3, you guessed it, 3. And when K is 4, 3. So we get 12. We've got some rules for finite sums and some formulas. You don't need to memorize these formulas, but you're going to need them for the homework, so you might want to refer to them. If you have the sum of an AK plus or minus a BK, you can break that up as two separate sums, add each one, add your results, and you're good to go. Any constant can come out of a sum. So this first formula here is a formula that we actually saw in action above. When we added the number 3, k equals 1 to 4, we got 12. And so this was just k equal 1 to 4 of 3. By this formula, we should get c, which is 3, times n, which was 4, and that indeed was 12. We're going to look at this example below, and this one you've got videos of in your homework. I'll just write homework videos. All right, so let's look at this guy. Add up the numbers from 1 to 50. So this is, if I write this in closed form, this is the sum, k equals 1 to 50 of k. So we're going to use the formula n times n plus 1 over 2. So n times n plus 1 over 2. All right. Well, n is 50. So this is going to be 50 times 51 over 2, which is 2 goes into 50 25 times. 25 times 51, quick arithmetic there, and you get 1,275. Okay, here's another one, slightly trickier. Find the sum k equals 3 to 10 of k. So that's 3 plus 4 plus 5, ... up to 10. Well, the formula n times n plus 1 over 2 isn't going to work because that one's designed to start at 1. So what we can do is think of this as 1 plus 2 plus 3 plus ... up to 10 minus 1 plus 2. So this, in closed form, this is the sum, k equals 1 to 10 of k. And then this, we can just subtract 3. But if this had been like a longer expression, like, you know, maybe 1 plus 2 up to 8 or something, then we could have written that in closed form, k equals 1 to 2 of k. All right, now we can use the formula on both of these because they both start at 1. So this one is going to be 10 times 11 over 2, n times n plus 1 over 2. And then this one is 2 times 2 plus 1, which is 3, over 2. We knew that was going to be 3. We didn't really need a formula for that, right? But this first one is 2 goes into 10 5 times. 5 times 11 is 55. And then I'm subtracting 3, so I get 52. You may have seen finite sums in high school, maybe not. Some teachers cover it and some don't. I want to give you a preview of the next section and talk about integrals. Suppose you got a curve and it doesn't necessarily lie above the x-axis. It might go above and below, and you want to compute the signed area under the curve. And by signed area, I mean anything that goes below the x-axis is going to count as negative area. Anything above counts as positive area. So I put the positives in green and the negatives in red. You can partition the interval from A to B into subintervals. So each of these has width delta x. And then supposing you pick a test point, C1, from each subinterval. Now that doesn't have to be a midpoint. I've drawn it so it's midpoints, but it could be any random point. So this would be C1. This would be C2. And the height of the rectangle is going to be determined by the value of the function at that point. So the area of rectangle 1 is f of C1 times delta x. The area of rectangle 2 is f of C2 delta x. Down here, when f of Cn is negative, then what this is, it's negative the area of the rectangle because the height is going to be a negative number. Now, if you add all those numbers up together, you get what we call a Riemann sum. And since it's a lot of adding, we like to use closed form with a sigma notation. The sum I equals 1 to n of f of ci times delta x. And if you use infinitely many rectangles, that's what we call the signed area underneath the curve. The true area underneath this curve, counting green as positive, red as negative, is called the signed area, and in the next section, we'll see that we call that the integral from a to b of f of x dx. So we don't use the sigma notation anymore when we take the limit as n goes to infinity. So we take infinitely many rectangles, we get what's called an integral.